it's not going. It's going to be like people that are a bit more experienced out of the way. Yeah, most of the time it's for medical students. Yeah. I'm in a bright room with computers that are very powerful. Hey, I mean, we can always play Plinko on the giant projector. There's a little bit right there. And there's a guy way up there. See it? I think it's easy anyways, too. It's not even HDMI projector, it says Thunderbolt 4. Yeah, take a look. Look at this. Newer. Right here. This cable right here is Thunderbolt. Oh yeah, heck yeah. This is a Thunderbolt cable right here. It's also, oh heck yeah. They did. They're also introducing the 14th gen CPUs. No? 14th gen's been out for like, they released like the 13900, 1300K, 1300KF, KH, and KS. Yeah, that was like year, that was like last year pretty much. Yep, like DDR6. It's been out for a little bit, but it's just like it's not worth getting it right now because it's unstable. Yep, DDR5 stable, then DDR6 unstable. Yeah, I see a painting that reminds me of you. It reminds of Jungle Mess. What? No, I had not. I mean, are you talking about me? Dude, one of my last projects was taking Java code and making a Python file out of it. I know Python's easy. No, what I did is I made it so that there's either presets or custom. You want to say like you just click one on your keyboard and then it'll type the entire print statement. All you need to do is say like what do you want to print. And you can do an entire if then else statements just by pressing your number. That's pretty much what I did. And it'll make an entire Python file for you. I see. Hey, how is your mom in the background? Yeah. Got that front end. I got the JLabs in. I don't know. JLab has great audio. I can listen to its own files and no problem. I can listen to the. I have JLab JBuzz Air Pro. I can take on the bus with zero audio issues.
Are you Nitish?
I am not. I'm about to go to class.
I'm sorry?
I'm about to go to class.
Oh, okay. Have a good time.
Is there anything I can help you with?
No. I think I'm okay for tonight.
Okay.
I think.
Good luck.
That's right.
Are you a comp sci professor?
Yes.
Oh. Okay.
Well, thank you. Have a good night.
You too.
Are you Wong?
Yes,
Did
Yong.
I get it?
Young.
Young.
Yes.
Young. How I say it? Y-O-N-G.
Yes,
Young.
Yong.
Okay. You keep correcting me. Just go.
It's okay. It's okay.
I'll catch it. Well, hello, Ahmad.
How are
you?
All right, great to see you again.
Hello.
Hi, how are you?
Good.
Should I get this bar?
So you decided to come back for another dose, huh?
Yeah, I need that.
Just couldn't stay away.
Yeah, I needed to survive.
Classes going okay for you?
Yeah, not bad.
Well, try not to burn you out tonight.
Yeah, I mean, I don't know like where the things are.
Yeah, that's already my living situation.
Okay, can I give you a pen? If you don't mind.
Yeah, thanks.
I'll get back to you.
come you're so quiet? I know. You just can't wait to get your fill of statistics, huh? When we come to the right place. People, rather than me pass this out, I have 7 sheets of paper from left to right. Want to come up and grab one of each, please? Are you Ryan? Did I get that right? I got all the pictures of the people, so I'm just gonna guess as they come by, okay? And let me think, are you Claire? Ah. Thank you. Hello, Sana.
Yes, you're good.
I guessed.
Yeah, you're good.
Just forgive me. You say hello to your advisor for me, Paula.
Okay, yeah.
Old stuff, huh? And you, Latish? I got it.
Like even Google says 90-ish.
Doesn't. What it is, huh? Well, I see 7 people, and I think I have 7 pictures somewhere around here. So welcome, everybody. Is it cold out there? It's inside, what is the temperature now?
Teens still?
20.
Anybody see the Kansas City football game the other night? Watch
Yeah.
football?
That was.
Want to be on that
It
field?
looked cold. You can see those guys. They look.
Yeah, but Kansas City didn't look like it bothered them at all. Steelers could have used a little warmer weather, maybe. So I'm Professor D'Amico. I'm the instructor for linear models and experimental design. And I see a couple of books. So everybody get my email last week? And that's one thing out of the way. So I will try to follow the schedule. And I know if you look at it from the outset, these topics should look familiar to you. And that's okay. Because when I started, pretty much, not personally, but personally with the statistics aspect of our computational math degree some 20 years ago, I really loved the idea of the degree. It still is valuable. But myself and another instructor, we kept perplexed because a lot of students would come and interested in moving on in statistics. Let me ask, how many are here considering that? After we leave, Ryan, you are, okay, anyone else?
Like specifically?
Pretty much, if you think you may get a job after you graduate, or even go on to graduate school and do statistics, or get a degree in statistics, that's what I'm pretty much asking you. Now, I know two students, Afsana and Young, you're in a whole nother program, okay? But that doesn't mean you're excluded, because you need statistics
Yes.
as much as I think the rest of you do. So whether you answered yes or no, and I only had a couple answers, it don't matter to me. Because my feeling with the program is I am going to try to prepare you for the day somebody asks you to do a statistics question. Until that day comes, okay, you won't know. Because at that moment, nobody cares about what grade you got, what your rank was, your QPA. It's all moot. Nobody has ever asked me, well, how did you do in graduate school? You get the degree, and that gets you into the door. So having the degree will put you into a room, and you are considered to be someone of certain knowledge that you can answer questions. I am going to address those questions. So personally, I'm a biostatistician. I've been doing biostatistics pretty much for over 40 years. I'm still doing it. I have multiple hospital appointments where I'm the director of biostats. I love it, okay? I'm no longer a full-time professor at Duquesne. I was for another 40. And this was one of the programs. This was these 2 semesters, this semester was the first class, I call it one class, that we introduced this to students usually at the second semester of their first year. Is that true, Claire, for you? Are you first year, second semester, second, Ryan? Okay, I don't care where you guys are, okay, because you're in, all right? And Ahmad, you're all right too. And so, this isn't enough. After this course, I said, so I was at another professor, John Kern. We were intent to make sure the people that did statistics in our program, they moved in continuity from one course to another. And we created 3 or 4 courses. And then students left, and they had a knowledge of when somebody, so they could stand. Could they do every problem? No. But they could stand and communicate. This class is about as much communication as it is about mathematics. And in fact, the mathematics is low key. Because no one cares if you can do differentiation. In medicine, I'm always asked, well, is that right? And certainly when I graduated, I didn't have the knowledge to answer those questions. Oh, I got the A's. Or somebody would ask, but I had to go look things up. If if you look on the next page of the syllabus, you will see my objectives. One of the objectives is to improve your basic understanding of statistics. Every course I teach is about understanding the basics. About 70% of the jobs I do outside of the room are fairly basic, but they're only basic because I designed them. And that's your next 7, 8 weeks, is design. So I will tell you a pet peeve, it's not really a peeve. Now, I could say it because I've done it, and I can do it. You may not have that prerogative in your first positions, but I don't analyze any data that I wasn't part of the collection. And because I've done so many thousands of projects, and in my earlier years, after I thought I was finished, a whole different set of rules came in. And so everything that was done was, Jesus, if I knew that before, I would have done this. But over the course of time, it came to me that we needed to sit down and just listen, and in my mind and in your minds, we process the information. And that's how I came up with linear models. If you were in a math stat program, linear models would be taught all matrix algebra. Sure, we could do that, but when you were finished, you'd have a good understanding of the matrices, but you'd be out there stumbling when someone presents a problem to you. I'm going to quiz you on and off, and I'm going to talk to you on and off. You got to talk back, okay? You got to answer. You got to try. And like I said, this is just the first one. You will see the things that I ask you aren't like other statistics teachers. There is a slight difference, and the difference is when I leave this room, I practice statistics. I'm no longer a teacher. There's a difference there. Our mathematicians are excellent. And that's what we do. We teach. But when you leave the room in the real world, again, grades ain't it. If you can't answer a question, if you don't even know what question to ask, and people believe me, it takes time. But that was the point of us creating these 3 sections. So this one, linear models and experimental design, was an introduction into a new way of thinking. When I get asked a question, Frank, I got this data, what test do I do? What test? In my mind, I will answer the question, but I'm also giggling, because I know the other person doesn't know statistics. Now, there's nothing wrong with that. That's why they may be asking me. But that's the wrong question for me to answer. And so my job is to get you to understand that statistics isn't about doing a test. It's about first stepping back and listening to the problems that are coming in. And in your mind, you should be thinking of models that might be appropriate for the data and the questions that are coming. I'm going to show you a question. I'll show you something that I consulted on last semester. You may feel off guard, we'll see. But, people, I'm not a doctor, okay? And yet, in the hospital, quite often I get questions asked, and I have to say, you're the doctor, because I will get asked, well, Frank, what treatment is best here? And should I use it? There's an important question. Should I be using this treatment? I get that asked a lot. And the answer depends on the data. How good is the data that I could make an answer that I feel comfortable with? And that's what it is. So these topics, I could come at them at any level. I choose to come at them as if this was your third course. So I feel I am correct in that. Afsana, I don't know your background, but you've had previous statistics classes?
Yes, I have.
Yeah, same thing.
Yes.
Aman, I know. Letitia, did you have, how many did you have Dr. Bush last semester?
Yes.
Yes.
In Markov chains
Yes.
and inference?
Yes.
Okay, so you won't see any Markov chains in here. You'll certainly see some things in inference spoken by another person. But then again, like I said, I can raise the bar. I don't choose to do it yet. So, for example, tonight is an easy night. It's about definitions that I want to get to you so that you understand me and the things that I am trying to get you to see. So it's about definitions, even though I've given you all these things. I'll briefly go through them and then I'll leave you alone. So this is my feeling about this evening. Usually about an hour and a half is when I start to see blur. And so I take a few minutes, we can take a break then. And usually I'll go always late, but tonight I'd like to finish about 8 o'clock. I won't give you the break. I'll go about 8, 8:10. Is that okay with
Yes.
you?
Yes.
Okay. So at that moment, I won't lie. Armand's giggling over there. He had me before. You know, you're stuck. No, I will try to be true. At the hospital, I'm on a time clock because they know me better. Oh, he's going to talk, you know. And the clock goes down. The girl in the back, she raises the flag. 2 minutes. I don't get that, but it's close. People. So each week, you can see here's my syllabus, same as yours, except I've highlighted in yellow. It's not important for you at the moment, but I am just showing you this because during these weeks, I am going to add to the topics that are in the book that you wouldn't have seen anywhere else. They're not in the book. And more than likely, I'm saying more than likely you wouldn't have seen them anywhere else. Quizzes, I'm pretty easy with grades. It doesn't mean you can't get away cheap. The biggest thing, again, you're all graduate students. I'll know if you're doing the work or not. You need to go home and you need to do the problems. You need to think, and that's the baseline. When you come in, you can certainly ask me questions. On page 2, I wrote my, my email is there, but also, I don't know, there's 2 to 3 days I might not be in town. We will still have class, I will do it on Zoom. I'm working not to do that, but right now I might have to be in Washington on a couple occasions. So, but again, I will still hold class. I will tell you, if the weather's terrible, how many drive? Does anyone else drive? Do you drive? How far do you come?
From the north side, not too.
Well, Claire, you're on campus or close by?
Close by me.
Yeah, Ryan, yourself?
I live in Southside, I just take the shuttle.
You're running over here?
I take the bus.
Okay. About how far do you commute?
I come in like 25 minutes, but I have classes these days. I
All
teach, so.
And, Elsana Young?
Oh, I come by bus from school. I think.
Okay.
I take T.
You come where?
I take T subway.
How is it? Okay. Well, like I said, if the weather were bad, I don't know, it takes a lot for me not to get on the road, but at the same time, I live in, near Butler, and I'm here early enough. So my office hours, people, you're always welcome to come. I'm usually here about 3:30, anytime
Butler is
before
like
class.
Freeport.
Pardon me?
It's the Freeport, Butler, Kettingen.
Not that
Kettingen,
way, go a little bit northwestern.
Northwest.
Yeah, so go up Route 8.
28.
28 sort of splits off around
Etna?
Etna, yeah,
Etna,
yeah.
okay. Alright.
Yeah, I go left and you can go right. Sometimes I'll even take the Parkway North and come in from that side. It depends on the weather. Forget the grades, people. You know, just get that out of your head. You know, this is about learning statistics. And I hope, I don't know what the state is. Like I said, this is just the first. The course to follow this one goes up another ladder, and that's called predictive analytics. And in there, I do a lot of classification, and we raise the bar on continuous data. And then data mining and is the third level. So you people that are first years, and anyone else could take that.
So those are the two.
Yeah, that is. So if you feel this was good, and that's offered next year, I will do it.
Where is the one to take the data mining course?
That would
In
be
the
taught 1 year
la-
from 1 year. It's actually a spring class.
Who was there for the last year? Like,
I was.
okay, you rejected me for data mining class. You asked me to get the statistical inference and this class
Yeah, and
was.
then take it, okay.
Yeah,
And that was correct.
yeah.
That was the right way to do it, you know, and it's not that you wouldn't have been able to understand. People, if this is the only course you take in statistics that is taught by someone with a lot of applied experience, well, I hope not. Whether it's me or someone else, I mean, you need to have, so I do probably, when I say I do, I go to probably 3 to 5 workshops every year. I'm not the instructor. Another expert in another area is there. And that is the highlight, you know, because I'm going there because in the hospital, I'm the expert. I will tell you what I've learned from medicine. When I don't know something, I say I don't know. I don't give advice, I don't make recommendations that I have not felt comfortable about doing so. And when I need help, I go find people. If I find a problem comes up, a model that I can't get convergence, or I'm sure it's over-parameterized. But yet I can't simplify, I can't do transformations, I go get help. That doesn't necessarily mean someone here. There are a lot of statisticians all over the world, and today we can communicate with them. A person who I have met, I can't say he's my friend, I've talked to him a few times. Joseph Hilby is probably a world expert in linear models. I'm talking about serious linear models. And he answers his phone from the beach in Hawaii. And every time I call him, which is maybe once a year, I'll call him and I'll ask him for advice on some complex design. Software is giving me contradictions. I'll ask him, where are you? Oh, I'm sitting on the beach here. Here, listen to it. And he's a good guy. There are things I expect you to know. They are basic, but the thing is, when you stand in front of people, what you don't want is you don't want to have a computer doing your thinking. Yeah, we got artificial intelligence. Yeah, you can go Google anything. But you're the one that has to explain it. And if you're working with a company, a client, a clinic, an organization, they wanna hear you. They want communication. You can't babble, you can't stutter, you have to be clear. And that comes from confidence and listening. And one best way is to be a teacher. Have you taught stats at all, or taught mathematics, Claire?
I was a TA for the algebra.
Just TA, okay, same thing about just TA, okay. Ryan, have you done any teaching at all?
I was a TA for undergrad stats.
Undergraduate, okay. So I'm talking about seriously coming up and you got the responsibility. Because it's a different feeling, okay? And whether it's basic math, but even if it is basic math, don't you become really good at doing basic math? And it's true with statistics. So I still enjoy doing these problems. The textbook, leave it over there. No, I'm gonna put it in the box. This is it. Did you buy it new?
Yeah.
Okay. You can always sell it if you hate it. I don't think you will. If you need statistics, did you pick it up, Claire?
It's not here yet, but I bought it.
Yeah. Did you buy it new?
Mhm.
Okay. I won't. How much was it new?
Like 100, I think.
Just about $100. Considering books came down a whole lot thanks to Kindle and then online textbooks, electronic formats. Things like this, when they first came out, were in the $200-300 bracket. So, if you look at the very basics, I know this author, he's retired now, Kleinbaum and Cupper. This book has been used in every graduate school, almost every graduate school, that gives degrees, masters and PhDs in statistics. And it is the third level. And I will tell you, by the time, if we could get there, to the third semester in data mining, we would be doing the material in this book in chapters 22, 23, and 24. And if I could get you to that level and show you, okay, getting the software to run and then interpreting it, that's pure linear models. So if you want to see where to go, just open the book. I think it's chapter 22 now. No, it's logistic regression. We could do that. Ordinal logistic regression. How many know what that is? Ordinal logistic regression. If you said yes, I'd be really surprised, okay?
I'm familiar with logistic regression.
Yeah.
That's about it.
Yeah, and you may have seen Logistic with Dr. Bush, did you? Was he able to get to it? I know it was in the textbook. Usually we can't. It was only 7 weeks, right? You had stat inference. No, isn't it? Because if you do it, you know, just fly right through it and then you learn it. When you do it on a computer, it's not something you can do by hand. I'm talking about chapter 24, but the real crux, if you want to really study, it's 25 and 26. That's as high level of linear models that we could get to. I am going to show you a piece of that at the very end of experimental design. The very end, okay, the last 2 and 3 weeks, when we get there, I will make notes and I'll say, okay, this is just a tab. People, I like to use Jump. Could use Jump software. Were you able to load it by any chance? Excellent, excellent. Jump is written by SAS. It's the PC version. We're up to, I know Duquesne, we get, I think we're up to version 15, but they're well beyond that now. And each particular version keeps doing more. I can almost do all of chapters 22 and 23 in Jump. And Jump requires you to know just a little bit about statistics. It will help you. So if you look at chapter 25, that is part 1, analysis of correlated data. And all I can say is, oh my God, okay? Because when we start to analyze correlated data, most of the general assumptions start to break down. Because, why do you think that's so? Because when we start to analyze correlated data, most of the assumptions that you've learned start to fall apart. I will answer that question later on, okay? But underneath it, it says general linear mixed models. That is called GLMX in R, SAS, STATA, and SPSS. It is GLMX. The models that you will be seeing are GLM, and that is called general linear models. General doesn't mean simple. There's a whole slew of practical models. There is another GLM called generalized linear models. And in generalized linear models, that is when, I'll just make the statement, and as we go through time, you can come back and ask me, but in generalized linear models, that's when the inverse, your independent variable, your independent data matrix cannot be solved. So if you can't solve if you have no inverse, what are you going to divide by to get your estimates? Well, that's why we have generalized. And I have to thank, over my career, I thank the computer scientists, the mathematicians, and the mathematical statisticians wrote the algorithms. You guys are studying algorithms now. Good going. But they wrote the algorithms that had approximations that could possibly converge and get real close to the actual McCoy. And then somebody started to computerize them. But we first had to have them in mathematics. So when I started statistics, I knew about all the models here, but I couldn't do any of them. Excuse me. I could do probably up to chapters 23, I think, 21, 22, something like that. We had crude software, and things have changed. Medicine has changed, thanks to us being able to solve equations and do simulations that we couldn't do before. And that's the beauty of it. It's beautiful. The science is so great. You can see I get excited, huh? So here we are. I talked enough about our syllabus. Let's move on. Couple of notes. I hesitated to do this. Chapter 0. I hesitated. I just wanted to first talk and say, well, but here there are a few things on this sheet that you need to start putting in your head, because every time we do a problem, I am going to ask you questions from this one page. So a statistical model, just think model, okay? When someone's talking, you think about the model. Well, what's going in your head? So what is going in your head is there's two sides of the equation. There's the left-hand side, which is y. I almost wrote on this. Imagine the kind of trouble I get in. I went the way I said, oh, I didn't do it. So just this little bit of news right here. Oh my God. Forget whether there's error or not. It all depends on what. But that little thing. So this variable, you've seen it. It's the d-netted variable. Give me another name for that.
Output.
Output.
Response variable?
What?
Response variable?
The response, I'll take that.
Yeah.
Output needs a little modification. So it could be your response variable. Another name. Starts with out.
Outcome.
Outcome. What is the outcome? So when I am listening and someone asks me, can you help me with a problem? I'm interested in doing something. I listen. If at the end of a minute or 2 minutes, I haven't heard something that sounds like the outcome, I know that I've got to help this person get focused. And that's the key. Because if we're going to study this variable, I got to know what it is. And you also have to know how it is defined. And then there's the other side of the equation. And these other things. So this function, even though we start off it in linear form, general linear form doesn't have to look linear. It just has to satisfy the requirements for a linear form. But this function, sometimes we estimate it, sometimes it is known, and sometimes it's our job to find out what is the best function. But these variables are your independent variables. And I'll leave that alone for now. And this, I would just say, is some random up or down value. We call it an error term, but it really doesn't mean something is wrong. Another name for the error might be
Residuals.
residual is a better name. Traditionally, we use the letter E, but residual makes a lot more sense. So here, a general model, this is what JUMP expects you to know. JUMP expects you, when you go in, and I'll show you next week, when you go into JUMP to do one of these problems, it's not going to ask you, do you want to, there won't be a pull-down menu that says t-test, okay? There won't be something called AOV, ANOVA, or linear regression. When you pull down the menu, there will be a command that says fit model. And it expects you to know which goes on what side. And if you don't, there is a platform for dealing when I don't know. But the key, and these are just the terms that I want to get, every variable on either side, every variable has a level of measurement. And there are 3 of them, and this is crude. Every variable. And this is information that you should know. So when I'm listening to a problem, and I heard something that sounds like a response, I would ask the doctors, I would say, well, how do you get that? Is it a result from a lab test? Show me what the result looks like. And the reason is I don't have to tell them that I'm trying to think of a model. I'll just say, I'm trying to understand the situation. So these levels of measurement will dictate where we go, how we're going to get there, and what steps do I need to take. When you've done statistics before, even calculus, all mathematics is pretty much like that. The data is given to you, even in the book. You know, you open the book, there's the data set. I am going to try to get you to the point to think, what steps do I needed to have done or to have advised so I could have gotten to that point, and then I could do the analysis. You go.
Professor, you question mark modeling data is all about studying question mark. What's the answer for that?
Yeah, that's a very good one. I will answer that one in 1 second. No, you keep doing it, because the reason I put a question there is because I didn't want you to read the question mark. I wanted to talk to you before. Your job is to answer that, but I'm going to wean it out of you. You say, this is me being tough, you know.
Tough cookie.
Yeah, but I'll go back there. Let's answer that since I had it down. So my question, modeling data is all about studying what? Wait. You see, whatever the answer is, it fits. If I said research is all about studying, and in fact, every summer, I teach a new group of physicians. These are practicing doctors. This is at UPMC. They're practicing and they're not quitting practice, but they come back and they do a fellowship. It's called an academic fellowship. They want to become teachers of other doctors. Not just practicing physicians, but they want to be teachers as well. And part of that teaching, I'm in control of their research. I'm in control of them reading the journal articles. I'll show you one in a minute. And I ask them this question. I say, well, what makes medicine so difficult? Is medicine difficult? What makes it so difficult? And then I will say, if you could sum it up, medicine is all about the study of. And that's the word, you see. Do you have a guess at that?
Yeah. I think modeling data is all about studying the data.
I like it. Can you be more specific?
Uh,
I like the answer. So is that what makes medicine so hard? Studying the data. It could, yeah, it could.
Relationships
What relationships?
between those things, the features, the
Okay,
independent and
yeah,
okay.
yeah, yeah.
The usefulness or implications of the data.
See, that's good. Yeah, that's good. I have a better word, I think. Claire, any thoughts over there in that corner?
Not really.
What makes medicine so hard? I will tell you, I carry that question all around me because that's one of the objectives of this class. Is I need to help you do that better. And almost inevitably, when I'm teaching and I'm talking to the doctors, okay, the clinicians, they will get the word. They will, and usually they will answer it, and I can pull it out of them, but I don't have to try very hard. Because they could say, well, of course, it's the variance. And that's the key. You see, modeling data is all about studying variance. Now, there may be other words that fit. Research is all about studying variance. I mean, why do we do research? We need data, of course, we need good data. But if every point were a constant, what are you going to say? It's the variability. And then the next question with disease is how come some people who've smoked all their lives have healthy lungs at age 90? Where other people who've never smoked died of lung cancer at age 45. Is that, well, you might say there's something else to it, right? But the difference is variance. Now think about the equation for variance. What is the equation for variance? This one, s squared. Let's say we're talking about a variable on the right-hand side. What is the basic equation to calculate the variance?
Do you want the unbiased estimator?
Yes, I do.
Okay. 1 over n minus 1
Yes,
times the sum of x of I, of x of I minus x
exactly,
squared.
exactly, yes. 1 over n minus 1, and then you have the sum of x of I, you can leave that off, x minus. So this is called the sample variance, I regard this, but variance, I just used the word when I said variance, and I talked about those two people. What was the word I used? Difference, yeah. You see, every time you get two numbers that differ, you could have substituted the word vary in there where they varied. You see, my job in statistics is about studying variance, especially in medicine. But I'll go as far to say, you know, I've done some quality control work for businesses, and guess what? Production management is all about variation in quality. Pharmaceutics is all about studying marketing principles, producing treatment effects. And if you look at the equation, you see it's something minus an average. So if this and this were the same, you could then say there is no variance. So now we need to collect this well, so that this is a good estimator of the entire group, and then we move down the path. If I could now proceed, thank you very much. I'm sorry I forgot that. And that's why I didn't want to just put the word down. You see that I didn't get a chance to talk. I didn't get a chance to stress to you on our first night how important variance is. And has anybody ever said that to you? You calculate it. I know all my Biostat 1 students and Biostat 2, they're probably sick of me because I keep asking them. But they need to get it, okay? This is Biostat 1. What grade am I going to get? Got to do it. What's the test going to be on? I'm going to say it's going to be on variance. That doesn't help them, but that's okay. There are 3 levels of measurement, and the reason these are important, they fit either side of the equation. There is, and this is sort of crude. When I say it's crude, a mathematician might not like what I'm going to put on the board, because their definition of measurement fits a whole nother paradigm. But in statistics, we can get by with 3. And so these are the levels. And they're actually increasing strength going this way. So nominal, simply this to name. Categorical. A nominal variable could be just simply categories. Hot, cold, male, female. These are just categories. I don't care if you put a number to it. We usually do because that satisfies regression techniques. 1, 2, but the number means nothing relative to measurement. Doesn't mean a difference. They're just 2 different categories. So the number might name a particular individual with respect to gender. It could be with respect. I don't even care how many genders there are anymore, you see, because it's categorical. Race, disease. You see, in medicine, there are books written on just nominal variables. And the reason is because it's easy. Let's face it. Isn't it easy to say, did I pass, yes or no? Everything could be simply binary. But this is the lowest level. And the reason it's the lowest level is because we're not really measuring anything. But it still has its own level. And we have enough to call it nominal. These are the 3 levels that are used in JUMP. You have to declare them, and then it'll go ahead. So the next level up, So I could do this. I could say, well, if I added a quality to categorical, I would get the next level, and that is called ordinal. So what am I doing? I'm actually adding some order to the categories. So whatever it is we're looking at, you know, if I'm in the next level, whatever it is, it's more than that one and still less than the one ahead. So in medicine, we have gradations. And so here's an example. Levels of pain. So we ask this everybody, how much does it hurt? You know, how bad? You got a headache, how bad is it? And we want to get to it. So here, a level of pain could have as many categories as you want it to be. So it could be no pain, I mean, that's a category. I'm free of pain, maybe I'll call that 1. How about calling it 0. People like 0. But the number isn't necessary. So, and then you say, well, I have a little, I have a lot, whatever it is. You see, so it might go up to 4. 1 to 4 on a scale of 1 to 4. Come on, every day Google asks you, when you buy something, would you rate your experience at buying it? What are the categories? Does it give you one? Does it give you? I'm trying to think of the last one. Rate my experience. I returned the item too. Rate my, I think there were 5-point scales.
Yeah, they keep it pretty simple. They don't
Yeah,
want to
yeah.
complicate people, you know?
Yeah. Because you already bought it. So you already crossed the bridge. Before, there's the probability, right? You get the pop-up menu on the side because of all your previous experiences. That meant there's a high probability you might like this one. So this is ordinal types of variables. Ordinal variables are nominal variables as well. Except if I went 2, 3, 4, what you know is if level of pain is getting worse, the worst it could be is a level 4. What you don't know from the ordinal is the difference. All you know is that 4 is more than 3. Is it twice as much as 2? The answer is no. It's just more. How much more? You can't say. If you could, then you cross the line into what we call continuous. So here, continuous, truly, if you could measure it, then we'll call it, in this class, we'll call it continuous. Blood pressure is continuous. Age would be continuous. Height, weight, glucose values, blood oxygen levels, hemoglobin values, etc., etc., etc. How much money you make, for that matter, could be considered continuous. It all depends on how much you're willing to stretch. And why is this important? This is important. You need to know a few things in jump. You need to be able to specify the right and left-hand sides of the equation. And if you do, then jump will give you, in some cases, 50 or more different modes of analysis that suit the bill. So either the dependent variable, it could have any one of these levels, and if you have one or more variables, it could have, each one of those could have various levels, and it's your job to know that. And the reason being is that's going to dictate the direction. There's one more word on the bottom. And the word is design. This in itself, I've given you the answer. And that was one of the reasons why I hesitated to give you the sheet. Because we're going to do experimental design. So the word design means one thing. And it's always in the back of my mind, always. Every problem, I will ask the question, well, I gotta think. Sometimes it's my decision. From what people tell me, from what people ask me, I gotta choose the best design. And this can get technical, but it's simple. It's how the data, this is as simple as it is, how the data is collected. That's called the design. From the very beginning to the very end, you've satisfied. So here, so I have an appointment in Georgetown. And in Georgetown, I do strictly randomized controlled trials. And those are experiments. In the university at Duquesne here, a lot of the data we don't do, they're not experimental. But with hospitals in the design, if it's an experiment, it's an RCT. And that means there's a specific design for randomized controlled trials. We have a goal. And so if someone comes to me and says, I want to do an RCT, can you help me? They've already told me the design. My job might be to determine if they can do it or not. Because there's a lot of things. Remember, the design, collecting the data, comes well before you see it in your books. The steps, and that's one of the questions I will ask you. Starting next week, I'll give you a few problems to do. You look at them. I will just tell you, the designs in linear models are mostly different than the designs in experimental design. And that's why I split them. I say, so there's two different sets of thinking going on.
Can you explain those one more time?
Sure. So look at the class problems, people. 3 sheets away. Do you understand what I'm doing right now? I'm quizzing you. I am trying to get a baseline set of knowledge that I think you have right now on issues. Now, of course, people, because right off the bat, other courses probably get you right into doing tests, looking at tables. It isn't that I'm not going to do it, I'm just not going to do it. Not at the beginning. So if you look at this here, let's go to problem number 3. And I'll tell you what, maybe to make it even more specific, hold on. Let me walk over here and let me make a statement. Let me say, look, there are 3 types. I'm going to quote it because this is so loose, but it'll give you the start. There are 3 types of designs. People, this is the lingo. This is the language you need. I don't care where you're headed. I don't care what your degree is. This is the thing you need to think about. Well, how are we going to do it? And then where is it going to fit? So the 3 types of design, one of them I will call I'll call it retrospective. This is, so just somebody saying, I did a retrospective study. I want to do a retrospective study. These designs are also called case control. I will bet that in your previous stat classes, I don't care where they are, I will bet you have seen data that was retrospective and never told. If I were there, I would have said it. I would have said, this is how that data was collected. So what makes a study retrospective? This is the key. When I ask you this, when you read it, the answer is, retro means to go back. Everybody remembers that. To go back in time. That's a bad memory, okay? Because it doesn't tell you what are you going back for. If you remember that you're going back, you're remembering the wrong thing. A retrospective design implies that at the very beginning, I'm standing right here in time. My study's already done. All the data's back there, you see it? This is present, past. So what makes it design retro? It's because the outcome has already happened. Ooh. So for example, I will give you an indication. Suppose I wanted to I'd go over to Mercy Hospital and I would ask, I'd get permission, of course, I would go into their cancer registry and I'd find out how many people in the last 5 years had lung cancer. And then I would sample all the lung cancers. You see who I'm starting with? I'm starting with people that already have the disease. If I go back in time and find a person at this moment in time with lung cancer, then I might match them with another person at that same moment in time from their registry who didn't have lung cancer. And then we try to go backwards. What are we going backwards for? I got a person that has LC and I have one who doesn't. So I go back in their records, what am I looking for now?
Whether they smoke.
Did they smoke? I want evidence of smoking. And those people that don't have the outcome are the controls. And it's important to get those people looking alike. I hope, that's the key. That's why it's called matching. And then we use multivariate type statistical analysis to control for the matches. That's a retrospective study. The next one, so this one is when we go back in time to get to the independent information. So this one, time has gone by us. The next design is cross-sectional. This is the one that Google asks you. Every time you buy something, it asks for your opinion. In a cross-sectional study, I will say it like this, it's a little crude, but in a cross-sectional study, time stands still. And so whenever I do it, at that moment I'm collecting both the independent and the dependent data. So in a cross-sectional surveys, set the bill. A survey is cross-sectional. When you buy something on Google, it already knows who you are, where you live, knows a lot of things about you. Everything it knows about you are the independent variables. Your age, your gender, where you live, how many TVs you bought, what else did you buy in the last year? That's independent. And then after you bought something, what does it ask? Are you happy? How was the experience? That's the outcome. But it pertains to what you did just 5 seconds ago. And that's why we call it cross-sectional. It's a slice in time. Just like a piece of pie. You slice it, there it is, boom. This type of design, you see, what I can't get, as we study them, I don't want to make too many comments now, but cross-sectional studies, we can't estimate probability in cross-sectional studies because there's no sampling. There's no randomness. People answer, people do it, so it's pretty much biased in a sense, but that doesn't mean we can't study it. There's just certain types of statistics that can't be used. Can I do regression? Can I do some of the principles in this book? Sure. But I have to understand what the objectives are and the ramifications. The third level These are called prospective. So in a prospective, the outcome is yet to happen. Where is it going to happen? Where? In the future. The future could be 1 minute, could be 5 minutes. A baby is born. There are two measures that are instantly taken. There is what's called the 1-minute APGAR score. And whoever delivers the baby, every baby gets a 1-minute APGAR. It's a scale from 1 to 10. Complexion, breathing, movement, symptoms, temperature, pressures, and it all adds up. Babies that are healthy have pretty much high APGARs. They got all the good things. And when the APGAR is low, it's taken again at 5 minutes. So if the 1-minute APGAR is in good shape, the baby's probably in good shape. The 5-minute APGAR, if that's done, the 1 minute wasn't promising. So the doctors, whoever's delivered that child, they've got a few minutes to get that baby back. Don't have long to play with. And so we hope we can get that baby. It might just need oxygen, might need palpitation, maybe movements, God knows I'm not. So these are 3 types of designs. Are they everything inclusive? No. Prospective studies. When I say the outcome is yet to happen, usually a randomized controlled trial. This is where we start with 2 groups of people randomly assigned to a treatment and a control, and then we follow them forward until a certain time lapse has occurred, and then we compare the rates. In a prospective study, these studies where the rate of occurrence happens, that rate could be considered a probability. How come? So we start with 100 people that gets placebo. They get whatever the current treatment is, the gold standard. And we start with a new drug, a new combination of medicine to maybe lower blood pressure in the first 30 days. So we have 2 groups that are both at risk of having a lower blood pressure. You see what I just said? They both are at risk right now. And so the outcome in itself is purely random. So then if it's random, we can use the rules of independence, we can use the randomization rules, and we can calculate the probability of the outcomes in both the groups. So I will just tell you, there are many types of regression models that I could use here. Many, many, many of them. It all depends on what the actual factors and variables are, and what I want to do. With that in mind, so my question before I said to look at example 3. So Cleve, you were asking me about the design, is that correct? Can I ask about how the data is collected? Look at question number 3 now. So I'll read it. A hypothesis of ongoing clinical interest is that vitamin C prevents the common cold. You've heard this? This problem's a little old, but and I will tell you the current data, some people think yes, some people are unsure. Depends on who you ask. Don't ask me, okay? A study is organized to test this hypothesis using 20 prisoners as participants. Why would we pick a prisoner?
Because they are complete in something like a laboratory condition.
Yeah, we call them closed. They're closed population. So if we're testing vitamin C and we give one group the vitamin C, well, we know who we gave them to. A person coming into our office, anybody coming through that door, when they leave that door, who's to say they don't go out and drink a glass of orange juice or something? So we can't control the conditions. Incidentally, I will make a notice here that we don't use prisoners anymore. This is not allowed. So this study, like I said, I'm using it so I could have said just what I just said. I said there's a purpose in controlling.
Could you repeat what you called them?
It's called a closed group because, you know, who gets the vitamin C? Unless they're getting vitamin C illegally while they're in.
Yeah,
You
doing
know,
something, yeah.
We pretty much have them buttoned up. Okay, and the same thing with those that don't. Animal studies, we do that a lot, but with animal studies, people, this is one of my pet peeves about animal studies, is those are the ones that get reported on TV, but they never tell you that the results come from animals. And so somebody extrapolates that, oh God, these animals got better. That must work for human beings, they have similar morphologies. And well, they don't analyze data unless I was collecting it. So at this point, so in this study, 10 randomly allocated to receive vitamin C and 10 are to receive placebo. The number of colds over a 12-month period for each participant is given below. A little fictitious here. So let's ask, what would this design be?
Prospective.
It would be prospective. So the outcome is a cold. And then we're gonna count them. What do you think the level of measurement is for the number of colds? And that's a good question. Would you call it continuous?
Continuous.
Can somebody have a half a cold? It's an integer.
So nominal, because they either have a cold or they don't.
Yeah, but we're counting them. So there's 8 or 4 or 5 nominal cases.
Continuous.
It's continuous because we can actually differentiate.
Yeah. So here's one of the cases where, depending on how many people with 10 and 10, I don't know. I probably would continue it. I probably would say it's okay to go continuous, because 8 colds is twice as many as 4. Now, want to argue that? I don't mean to say argue. You want to discuss that?
Like, there's definitely varying degrees of a cold, like some.
Yeah. Remember I said up there, over there, I said, how is it defined? How do you define a cold? You know, what procedures? I'm not gonna go down that path too much right now, but that's the idea. So the lesson from what I just said, and this lesson I will iterate throughout the next year or semester anyway. The lesson is when you look at the data, before you ask or you answer, you should probably ask yourself, do I have all the information? You see, so I would have, if I were designing this study, colds and counting the number is the outcome, I would make sure that I had an individual who knew what a cold was, first of all, maybe even in the prison. And these 20 people, whenever they felt sick or whatever, they report to this individual. And this is me controlling the situation. And in fact, it isn't that I want to decrease the number of colds. My job is to collect the correct data to answer the question, is vitamin C the key? Well, the first thing it is you gotta make sure that you know what a cold is. So who's ever doing it, when that person reports to whoever the observer is, the observer writes a number down, yes or no, scores it, and that information is never given back to the patient. And it's up to the nurse or whoever it is that's doing the counting, whether they should give this person aspirin, maybe they're having a fever or some antibiotic, depending. It wouldn't be for a cold, but they might consider it more influenza or something more bacterial. I don't know. But these are things we would review. So this would be prospective. How about example 4?
Professor, what's the number indicating here? Like they are indicating the number of doses?
No, the number of colds. So this person, number 1, that got vitamin C, over the next 12 months, they had 4 registered colds.
Very good.
Person number 2 didn't have any. So people, if you were to indicate that number in jump, person, so you had a column, like in Excel, person 1 to 10, and then you had another column, person 1 to 10. Jump would think that person 1 is the same individual because you gave them the number 1. You identified them. Person 1 to 10 is what kind of variable? That one, that column right there,
Just nominal,
is
just a
pure
label.
nominal, right? That's pure nominal. But Jump doesn't know it. It's a machine. You gave it 1, here's 1, they must be the same. And this could lead you down a track. So I will show you how we code this information later on. People, what kind of tests would you use to first of all, what would be a null hypothesis for problem 3?
Vitamin C does not prevent common cold.
Pardon?
Vitamin C does not prevent common cold. Null hypothesis.
Maybe. So let's get some more rules down. I think we need a few more rules. So, when I ask you about hypotheses, they should always be in terms of the parameters, not the statistics. What's the difference between a parameter and a statistic? So here's the situation. There is this group that we always study, and we call it the population. So in the population, there are all these people, and each of them has a certain number of colds. So in this particular case, if I want to study, I need something to study. So I'll say, well, let's get the average. The average number of colds. And if I'm dealing with the population, there is such a thing as the average number of colds. we give numbers in the population, Greek letters, that would be called mu. So mu represents the true average in the population. This is a parameter. Most of the time, we don't know what the true population is. So how do I go about doing this? The idea is if I want to study vitamin C, I'm going to take a sample of people, whatever, no cold, and that sample of N, there they are, 10 people. And then I will measure each number of colds, and I calculate, at this point, I don't care what letter you use. Y bar, X bar, I'll use Y bar since it's the outcome. So this is a representation of all the people in the sample. That's your sample. And this is the sample estimate of mu. This is called a statistic. So statistics come from samples, sample data. Every problem you do is not a population, it's sampled from some population. But our goal, the goal in statistics, that's where the hypotheses come in. The goal is to make an inference. It's an inference about the parameter. Armand, you remember what the definition of inference is?
Making conclusion from a smaller size population or sample and replicating it to bigger population.
Well, I like it a little bit more technical. This is the goal. Almost. I'll hit you up on this one again, okay? But let's ask the question now. I asked you, what is the null hypothesis for this problem? So if you could see in your mind this situation, there's a population of people that are going to get vitamin C, and then there's another population of people that aren't going to get vitamin C. Go ahead then.
Would the null hypothesis be mu equal to 0, i.e. the average is no one has a cold?
Almost.
Okay.
It wouldn't be mu equals 0, because I have two groups, right? So we're testing cold.
The difference, mu sub whatever group 1
That's
minus
right,
mu sub
that's
2
right.
equals 0.
This is the simple t-trace, right? And that's the key, that's the recognizing part that I try to push you on. I say, here's the situation. Okay, you think about how to collect it. So the null hypothesis here would simply be HO. Under HO, there is no difference in the average number of colds. So we would say mu1 minus mu2 equals 0. Alternatively, they're not equal to 0. And so when I asked you and I said, hypotheses are always stated in parameters. This is what I want to see. I want to see, well, what's the parameter? Because that difference represents,
The number of cold, average number.
and it represents the, yes, the
Variation?
Variation.
the variance, and it's the variance, that's the whole point of the experiment. Let's go get it. Now, all of everything I've said would have gone through my head. Very little. If you ever saw my notes from a discussion, they almost look more mathematics. Because I know if this person is, you know, so let me think about different things. From the mathematics that I could listen and create, I know what to ask them in the next case. So I would say, well, how hard is it to get 10 people and 10 people? Can you confine them? Would they agree? What are we gonna do for them? Et cetera, et cetera, et cetera. Because anything that could affect that difference diminishes my ability to make the decision. Question number 4. So the birth weight of an infant has been hypothesized to be associated with the smoking status of the mother during the first trimester of pregnancy. This data is real. Okay, this is real data. The one before, I substituted it. Excuse me, people, I'm not answering this. I'm just shutting it off. Pardon me. The hypothesis is tested by recording the birth weights of infants for all mothers who register at the prenatal clinic at a particular hospital within a month, 1 month. Mothers are divided into 4 groups according to their smoking habits. And the sample of birth weight in pounds within each group is below. So, where should I begin? Let me ask you, what's the design? Remember, you're seeing the final product.
Right.
So, who did we begin with? We began with mothers who haven't had birth yet. We said it was within a 1 month period, maybe 5 weeks, maybe 6 weeks. And at that point, we record whether they smoked. So we said they're divided into 4 groups. They weren't randomly divided, were they? You couldn't take a mom and say, you gotta go smoke up a storm. The mothers are divided according to their smoking habit. We have non-smokers, we have ex-smokers, sometime in the past, we have current, and less than a pack a day, oh my God. And we have mothers who smoke at least a pack per day. So, this is the birth weight. The design would be prospective. What were you saying, Cliff?
I said ordinal. There's a degree of difference between.
Well, careful. What's the outcome?
The birth weight.
Birth weight. Do you measure birth weight? Sure. Mother has a baby, boom, put them on the scale.
That would be continuous.
It would be continuous, yeah.
Continue.
So the dependent variable on this problem would be a continuous, it'd be the birth weight. So this is where I see the question, here's the birth weight, and I don't know yet, is it a function of the smoking? And how is smoking defined? It seems like it's defined as a nominal variable. Because they either do, they don't, there's categories, etc. So this is nominal, and this is continuous. What's the null hypothesis for this one? And yet, everybody in the room has done this test, you see?
Smoking reduces the speed of treatment.
You gotta give it to me in terms of the parameters. It actually looks just like the one before. You see the outcome. This is where you choose your statistic. Good, right?
Would this be an ANOVA test?
It would be, yeah.
Because you're comparing means
of
your
multiple
means of multiple
groups.
groups.
Yeah, so what's the null?
It's, say mu1 equals mu2 equals
Correct.
mu3.
Correct. So there's 4 groups, mu1 equals mu2 equals mu3 equals mu4. Now you could tell me in words, under the null hypothesis, what does this mean? Put this in the whole context of that functional thing I have. If this were true, I shouldn't have said that.
Smoking doesn't affect the.
It doesn't appear to be different by the categories, yeah. Excuse me. What are we talking about? Birth weight.
Birth
The weight.
So the average birth weight of a child doesn't seem to be dependent upon the smoking status of the mother. Now, that's if we don't. So what problems do you see when you look at the data?
For starters, there's 7 in one group, 5 in another, 7 in another, and 8 in
Okay.
one.
So, I'm not saying you can't do the test, but you should be aware that there was no randomization depending, so we took pretty much a sample of mothers who showed up. Maybe that's not a good example of data, I don't know. I'm not saying you couldn't do the test, but you should be aware that if you failed to reject this hypothesis, what type of error could you have made?
Type 2 error.
Type 2 error. So, that's very good. Good. So you could have made a type 2, which means you accepted the hypothesis when they're really different. But the data wasn't strong enough to say it. You see it? So if you made a type 2 error, what other thing would you know? So this data has low, what?
Low power.
Power, you're right. This data probably has low power to detect the difference. In which case, that's because the sample sizes are unequal and they are small. Rules change as n goes up, right? As n goes up, you get closer convergence to the truth, and we're in good shape. Okay, how about, let's do one more of these. So if I did one more, let's do example 2. So example 2, one method for assessing the effectiveness of a drug is to note its concentration in blood or urine samples at certain periods of time after giving the drug. Suppose we wish to compare the concentrations of 2 types of aspirin, A and B, in the urine specimens taken from the same person 1 hour after he or she has taken the drug. So the things like 1 hour after, that wouldn't be a decision I would make. That would be the clinician or the pharmacist or the pharmaceutical company. They would be the one to best know that after an hour, that's when the aspirin has the most chance to have been absorbed in your stomach lining and get into the bloodstream, or excuse me, in this case, get into the urine. So 1 week later, after the first aspirin has presumably been cleared, the same dosage of the other aspirin is given to the same person, and we do it again. Since the order of giving the drugs may affect the results, a table of random numbers used to decide which of the 2 types of aspirin to give first. I added this to challenge your knowledge and your understanding of the word design. So how the data is collected So that last statement would be important. And this is a good time, you know, if this design has excellent power.
Yes.
And we'll get into that once you start studying linear models. I say, look, I'll show you the linear model with and without certain information. And then we'll compare the results. I'll only ask you one question on this one. My question would be this. What are the degrees of freedom that the appropriate test would have?
8.
I didn't say yes or no. I'm just listening. Okay.
9.
9.
So that brings up another thing that I didn't put on the sheet that I will now mention. And that is called the unit of measure. So the unit of measure, in actuality, it is the smallest unit of subdivision that we would use to input this data. And when you study it, it looks like this. So you have person, and it goes 1 to 10. You have aspirin A and B. If you look at this data and then turn the page and look at problem 4 again, or 3. They almost look alike, but they're not. In this problem 3, what purpose does the individual person add to the experiment, to the study?
Whether they had a cold or did not as a result.
So for the example 3, the populations are 20, but for the example 2, they are 10, and they are testing different drug in the same person.
That's correct, John. So if you look at this data, person 1 to 10 and person 1 to 10, these are different people. So how many measurements do we have on each person with vitamin C? And how many measurements do we have with each person on the placebo?
2 or 1.
1. You see, so there's no variability with respect to the number of measurements we took. So the unit here is the actual single score from each person. So this set of information, the person doesn't, we don't need it at all. Because ultimately this is just 20 people. These two groups are independent. So we have 20 people here, 20 single scores. Going back to the previous page, and now looking at example 2, we have person 1 to 10 again. Oh my God. But in this particular case, on person 1, we actually have 2 measurements. So these 2 observations are not
Independent.
Independent. They are not
Yes.
independent. There is a relationship. So I can't break that relationship. So in this case, the unit is the pair. And this is the way I see the data. So there are 10 pairs. And that's why I'm sure if I asked you to do the test, you would say, well, that's a pair t-test. And so that's what gives you the authority to go into this person. In the first case, these two observations belong to that individual, and take the difference. You get the first difference. So at this point, the unit is the actual individual. Just suppose I could expand this and say, oh my God, what if there was another type of aspirin? So I had an aspirin C. And I waited till B went away, waited another week, and I randomly assign everything and do it on. And I would have this. What's the unit now? Well, I'm glad you didn't answer, because the unit hasn't changed. But now the analysis, this would be entirely wrong, you see. You can't take any differences here, because you have more than two observations. When you only have two, there's only one difference. But if you have three or more measurements, there's multiple differences. And those numbers are could be. Those numbers are correlated. And so if you would have answered and said, well, they're not independent, that would have been right. So this was fun. I can't do them all. But the whole point of this was all of these problems, people, could be answered using linear models. So that simple chapter on regression, okay? In just a month, that's things that you've done for regression. With correct and understanding of parameters and what choices we have to go in, I'll show you how we could have done this. And so what is important is the linear model. And say, let me go back to y is a function of x. This will become the model. And it takes various forms. And there are multiple ways. So analysis of variance, we did that over there with the 4 groups, wherever it was, 4, up there. T-tests, pair T, they're all linear models. And I don't need to know those. I need to know how to write the model. I've got about 10 minutes. So I will, I'll tell you, this problem that I want to look at is so good, because it looks like it's way above your head when it isn't. And it's this example called poem on the top. Let me see if I can talk about this for 5 minutes, and then I'm going to wave my hand at the other 5, because you people are so good, you know. So this is the problem. It's called a poem. It's a summary of a design. get a few of these a week. I read them quickly, and sometimes I look to see how many I might be able to bring into this class. This was one that I asked to comment on the analysis and the results. So you don't have to be a physician to get this. You just have to have a few terms. And things that I don't understand medically, I ask. I said, no, you're giving them a treatment. What the heck is that treatment? What's it supposed to do, et cetera, et cetera. Okay, I got enough. I don't need to understand the medical. That's the doctor's point. That's the clinician's. So right now, adult thymectomy, that means removal of the thyroid gland. The O-N-Y means take it out. Usually it's surgical. So we take out the thyroid. Read the title. Adult thyrectomy is associated with increased risk of death. From this title, at the end of the semester, you see my circles over here, I would hope that you'd be able to write a model just from the title. And give me an idea what the design might be. And there's a key word in here that cues it all, that sends it all. So let's just read a few minutes. We'll just go through. And it says, clinical question, what is the impact of removing the thyroid on the health of adults? People, we just don't make decisions. I think I'll take your thyroid out, you know. There are usually clinical symptoms. People are feeling fatigue. They're not ill. Sometimes their legs are built up with fluid. And general malaise. So a physician will then test. We'll just check. I just feel your gland to see if your thyroid is swollen. It's a good indication that it's probably not working or functioning, and then there are tests. So the bottom line, this is the summary. The bottom line says maybe that thymus is busier than we thought. Remember, this is a review. So this is a review by a clinician that is sent out to groups of clinicians pretty much all over the world. And at the clinics I work for, okay, they will get questions. Now, they're primary care doctors. So they should be involved in diagnosing that this patient that has these symptoms, that's their first line. People don't pass out with this, they get sick. So you go to their doctor, and the doctor will ask for symptoms, and they will know, believe me. They will know, well, maybe your thyroid is enlarged, and they will check for it. So the bottom line is, this is what they know. There's a clear association between taking the thyroid out and increased risk for all-cause mortality, cancer, and possibly autoimmune disease. So here's the dilemma. Should we take it out, you see? If it's not functioning, well, so the implications for surgeons are clear. If you can, avoid cutting it out. For a primary surgeon, that's what they will do. They know they can do it. But then the question is, should I? For the primary care doctor, so the person shows up in the office, that's a little question. The primary care doctor isn't going to be the person to take the thyroid out. They may try to determine if the thyroid is functioning or not before they send them over to the surgeon, who will then remove the thyroid. But from the title, it says it's associated with increase of dying. Now, I don't know what those increased risks are. And cancer, it sounds bad. However, this is why you need to look at the data. Because, okay, I'm going to jump to the next page. There's your results, the top of the next page. I could spend an hour talking to you about statistics, design, levels of measurement, and never go any further than this paper. I could do the whole period. Because each sentence builds on things that we do in mathematics. And the more you understand how the mathematics could fit together, the easier it is to take the place, because it's not difficult, it's understanding it. So somewhere down the page, about halfway, starts the sentence that says, all-cause mortality at 5 years. You see that line? So it's about 3 or 4 or 5 lines down in the first paragraph. And on the right-hand side, that is the beginning of the results. These are the numbers that I was asked to contribute, put it that way. Because these are the numbers that come up with the bottom line. This isn't a conclusion. You do a t-test, you get a p-value, there you go. Remember, you need to stand back and understand the process. So here's the data. With respect to mortality, all-cause mortality at 5 years was significantly higher in the thymectomy group than in the control. And then they give you the rates of dying. 8.1% versus 2.8%. What do we know about those two numbers? What would you call 8.1% and 2.8%? What could you call them? Spit it out. What do you call them? I wrote it over there.
Difference?
They're what, Amand?
Difference in ratio?
Well, they are, yeah. Another one.
Continuous,
What?
like, are you asking whether they are continuous variable?
Would you call, this is the rate, these are rates of dying, would you say that was continuous?
It is.
If you had multiple cases, but this is one case, right? This is one sample. Thymectomy, 8%. So they either died or they didn't. No, that wouldn't be continuous. I almost said it.
Yeah. The level measurement is on that just normal.
Yeah. Keep banging that thing. Let's see. Looks good to bang too, sure. When I asked you what they are, you got the point, but they're statistics. These are the statistics, right? Those are the numbers that we are going to use to see. So what we see is there's a difference of nearly a little more than 5%. You see it? And then it says relative risk. We'll go back. 8%, 2.8%. Those are statistics. What do you know also about them? They are significantly different. It says so. They were significantly higher in the thymectomy group. What does the word significant imply?
So in this case, like with the risk ratio, it doesn't include the one in the confidence interval.
Well, that's beyond it, but that's right, Armand. That's done. The word significantly implies, you don't see it here, but you could have done it. This would have been
By chance.
a chi-square test for two proportions. P1 equal P2, rates of dying. You would have done, so significantly implies that a statistical test was done and the difference was found to have a p-value of probably less than 5%. The relative risk is 2.9. That is a way in medicine of measuring the impact of one group to the other. We take the ratio of those two statistics. 8.1 divided by 2.8 is about 2.9. So in the literature, this is how I listen. And I advise how to interpret from two clinicians. I listen to how they want to report this. And I could also say, you know what, the group that got thymectomy were 3 times more likely of dying. Approximately 3 times. And that was significant, probably at p less than 0.05. So keep going all the way down to the bottom line. I'll read the last sentence. It says there was no difference in the likelihood of autoimmune disease in the primary analysis. But after excluding patients with preoperative autoimmune infection or cancer, the author saw an increased risk of further autoimmune disease. Again, 12% in the thymectomy group. And it gives a relative risk. See, the ratio is only 1.5 there. And that 1.02 to 2 is the confidence interval. And it's pretty close to 1, isn't it? It's really close to 1. So, I mean, I guess if you want to say it was significant, okay, I probably wouldn't stretch it. My question to you is the next statement. Because you see the next statement there? That is something I would have written. So when I do a study like this, when you do a study like this, you want to be the last in charge. Okay. When I do analysis and then I give it to my people and they write it up, I want to be the last person to edit. And this is where I want to be very careful and correct in the interpretations. And then I would have added that last comment. Given multiple comparisons, however, this should be considered exploratory. Do you remember what multiple comparisons are? Have you seen multiple comparisons? There is a multiple comparisons problem. You will first see it. Okay, that's okay, I'm just asking. Okay, you will see it in chapter 17. Multiple comparisons. Look, p-values, this is the most difficult thing I have in the hospital. Trying to explain to clinicians, look, you keep testing, aren't you going to get false positives? You keep checking, and then when you get one, what are you going to do? Oh, I got it, he's wrong. What if you're wrong? And so I will advise my clinicians, I will advise them, look, don't order the test unless you're going to use the result. And tell me how you want me to use it. Because if you order 10 tests, then you're only going to look at the ones that you like. Well, don't worry, it doesn't happen, okay? Because I don't let it. And that's the whole thing. Multiple comparisons is an issue that will come up in chapter 17, and I will cover it. People, I want to zoom to 2 things. I'm not going to do this, okay? But if you zoom to my notes, this is my notes on regression in chapter 5. The next page is the homework from chapter 5. So I've asked you to carefully review the chapter. We will spend probably a month on this chapter. Even though I'm moving forward, you look, you see what we do, 6 and 7. I haven't forgotten, there's 30 problems in this chapter. And many of them are very good. So I've only asked you to do 3 of them. And so I've been specific, but I want these done by hand. I've picked ones that are manageable, I picked ones that are unique, and I picked ones that I could carry the ball next week. I pick up the level, I say, hey, did you notice this? Did you notice this? So the first problem, number 4, part 2, I said, load this data and jump and run the model and obtain the printout. You can hold off on that. We'll do that in class next week. But to do the rest by hand, just follow my notes right here. Everything on these 3 sheets, by the end of the semester, I will expect you to know. For our first quiz, I'll expect you to know these equations. They're not hard. These are equations dealing all the time with just calculating variance. But I've tried to be specific going down, and people, I have a correction. You see in the first page where it says beta O and beta 1 with the equal sign, it should be this, right? It should be beta O hat. Those are estimates, beta 1 hat. That's how we define an estimate, the statistic. So this is the statistic. Beta O is the parameter. Good. So I've asked you to get, just sort of to get loosened up, okay? 3 problems. The thing is to study the material in the chapter. Next week I'll add more problems from chapter 5, a little bit from chapter 6, and me opening my mouth some more. And we keep going, moving up the bar. But you won't go a day, okay, without me asking you about the design, without asking you about the level of measurement, hypotheses, because the conclusions have to be stated correctly. Not, you don't want to write a sentence that says it was significant. Oh, it was significant, but was it significant? It was significant. In the hospital and in literature, people, I have to let it slide a lot of times because I become boring saying no. The problem is people use the word and don't even know what it means. But it's important. And you should be better than that. We need to be better. Not just you and me. Yeah, we need to be better. I keep minding myself, remember. And it's not like I harp on everybody in the hospital. There are things people say, well, he hates those. Because it's the mistakes. We calculate p-values a lot. Think of how many problems that you've done in the past, how many you've yet to do, where you don't calculate a p-value. I would just tell you, I use them, but I don't like them. And in the future, you'll see why. But you don't have to listen to me, remember. I'm just teaching you and giving you my advice. Hopefully it's good. Okay, I promise. Look, what was my standard error, Mark? You can't, all the time. Okay, we're concluding. I will see you guys next week. We will be here.
Officer, two questions.
What's that?
Like, two questions, like, are these the ones to be completed?
Just, you see, this, yeah, I want you to do all of them, but the only one I wanted you to do in jump, not to do in jump, is this one.
The question report.
Yeah. But the rest, yeah, you